And today I'm going to talk to you about driving innovation with high-resolution CFD or computational fluid dynamics. So just a little bit about a background about us. We are aerodynamicists and thermodynamic experts. And before I get to a few case studies of how we've applied our technology to provide energy efficient savings for products, I want to give you a bit of context, a bit of background of why we're doing it. So just 50 years ago, we finally ventured to the moon. For the very first time, we looked back at our own planet. Since then, the human population has more than doubled, our energy consumption has more than doubled, and our CO2 emissions have followed suit. This is a graphic of the temperature anomalies of the Earth from 1880 to present day. And it's compared to an average of 1950 to 1980. And it shows an increasing temperature. And if we just look at the next graphic, we're looking at the average temperature increase from 2014 to 2018. Now, this is a stark graphic showing a significant increase in temperature. 4 degrees Fahrenheit is around just over 2 degrees Celsius. And a little bit more evidence of what's actually happening to our planet can be found in this graphic, where we're looking at a number of different sources essentially providing the same evidence of a global increase in temperature. And this is from NASA, NAO, Japanese Meteorological Agency, and UK Met Office. So there is a significant change in our planet as we go through time. And if we think about CO2 emissions in themselves, it's interesting to look at how they've changed in time as well. This is looking at the CO2 emissions created in the world over time, and you can see that it's a very interesting and actually almost mind-blowing change over the past 100 years. So let's look to the future. What's it going to look like? So many of us have heard the term 1.5 degrees and 2 degrees and how that's going to change the Earth. But actually current policies look like the Earth is going to be more in the region of 3 degrees if it tails off. So 4 degrees, what does that, or 3 or 4 degrees, what does that actually mean? So an interesting comparison, a reference point for this is the last ice age was only about 4 degrees cooler than the average temperature of the Earth is now. So that puts that into perspective, that just a few degrees changes have a significant impact on our world. But it's okay, because we have the capabilities to do something about it. Together, engineers and scientists can create innovations that can change what we do and how we live and how we work. We are doing more to do with clean energy. Pretty much every day you see a new article about an increase in solar PV cells or wind turbines. And that's great, that's fantastic. But when you look at the bigger picture, in terms of the global primary energy consumption includes the actual energy creation itself. And actually, we're only working at about 11% renewable energies. So something needs to change, something needs to happen. And we, as engineers and business leaders, need to act. One way that Wirth Research and our capabilities and what we're trying to do is create significant changes in energy efficiency for products and systems. When you kind of step back and you look about the innovation around the world at the moment, there's autonomous cars are being created, and there's huge inroads into that. We've got space rockets that can now autonomously land themselves. I mean, the capabilities that we have at this time right now is just incredible. And if we focus that capability and that skill set, we can really make a significant change in the next 10 to 16 years that we need to do. So I want to move on to a couple of case studies, but before that, let me introduce you a little bit more about what we are and what we do. We're aerodynamicists and thermodynamic experts. Over the past couple of decades, we've created our own HPC, or high-performance computing facility, and we are using simulation as a driving force for change. We are using the ANSYS Fluent CFD solver, the industry standard or industry leader in simulation capability, and we wrap around automated services or automated processes around that to really reduce the amount of human input required into that system, which means that we can not only get the benefits from simulation to be able to identify a root cause of a problem, but we can also develop solutions very, very quickly. And we developed this in motorsport. So for a number of decades, we've been working with a few partners in the States to develop a sports car chassis and also IndyCar aero kits as a few examples. And the left-hand image here is of a sports car. It's the lowest surface of a sports car. And you can see it's obviously incredibly complicated airflow, but what high-resolution computation and CFD allows you to do is to get really accurate results, to make you really understand what's actually happening in the airflow so that you can optimize the geometry to make a car go quicker around a track. The right-hand image there, which is now stopped, is an IndyCar. It's a very, very different car. This needs to go up to a speed of 240 miles an hour around an oval. So it actually requires very different aerodynamics. It's not as much downforce to make it stick to the track, but a lot more slippery, a lot less drag. But you've got these huge wheels in the way, which is one of the causes of the main causes of drag. And in 2009, we actually switched fully to development using CFD as opposed to using model scale wind tunnels. And the reason for that is because our correlation to real world conditions got to the stage where we felt we were able to do that. And so just a little bit of background on our experience. We've been working with Honda Performance Development since 2004 and supported them in winning multiple championships and IndyCar 500s in the States. And also sports cars as well, so the closed wheel racing that I talked about earlier, which also were races in the States, but also in Europe, in Le Mans, so 12 to 24-hour races. And we were the first F1 car technical partner to design an F1 car using CFD back in 2010. These days, CFD is much more a part of F1 racing than it was back then. So around 2010, we looked at how we could transfer what we'd learned in motorsport and the experience that we'd learned in motorsport to make a car go quick around a track to other sectors. So can we make a truck run more efficiently by reducing the drag? So we approached Eddie Stobart and we showed him our capabilities in motorsport and what we'd learned and what we'd do and how quickly we can work. And he was interested to take this further. And we used our experience from laser scanning tracks to laser scanning a truck and converted that into a 3D model and then blew digital wind over the top of it. And this is a bit of an output from that development. And you can see huge amounts of detail in the airflow around the truck, but there's actually it's very, very draggy. You can see these structures over the top of the trailer, which basically one of the main forms of drag for a truck. So we applied ourselves into trying to develop aerodynamic kits for trucks. A little bit less exciting than motorsport, but still the outputs can be really game-changing. So we created a number of different components focusing on when the drag was being generated. And these are, some of the components that we created at the very early stages. So we've got our trailer side panel component in there. And some of these components work straight ahead, some of these work in crosswind to really give the overall performance that you need in real-world conditions. And we ended up with this configuration, which was mainly a spoiler on the roof, a trailer side panel in between the cab unit and the trailer itself, and a few leading edge devices on the trailer, on the truck, to try and control the airflow at the leading edge. And this was trialled at a number of different independent tracks around the UK in long-haul drive cycles, and provided the savings we were expecting from CFD, and that was around 10 to 14% drag reduction. And then that was taken to the road, where we did a 6-month road trial on 20 trucks, covering around 500,000 kilometers. And again, saw the fuel savings and the drag savings that we were expecting. And that kit can be seen on a number of Eddie Stobart's fleet and a few others around the UK. And we've moved on to other kits and other ways that we can try and save different configurations of trucks and trailers to save fuel. And this component itself is actually the two components on the front. So the bubble at the top and the second component below actually gives a saving of 5% fuel saving on this tall trailer. So this is a 5-meter trailer. The ones previously were a 4-meter trailer, more consistent, whereas these will be applied to the much UK-based tall trailers. So we've been talking to many logistics companies and retailers about how we can save them fuel and energy to really reduce the CO2 emissions they're creating. But some of the feedback we got from retailers was, we've got another problem. It's these things, our fridges, or formerly known as open-fronted refrigeration display cabinets. So, as you might know, when you go into a supermarket, it's very cold around these aisles. And the reason why it's cold is all the cool air that's used to try and keep all of our food and drinks cool in the fridge is just spilling out into the aisles. And there's no wonder there's no doors on, right? So actually, when you look into this, it's a very, very big problem. Supermarkets account for nearly 7% of the UK's energy. That's a massive number. Well, 7% isn't big, but 7% of a large number is a very, very big number. And refrigeration accounts for 60% of this. So if you could make it infinitely efficient, then you would save the UK 4% of its energy, which is an interesting thing. So we continued discussions with some retailers, and they managed to give us an old fridge, still with the stale sandwiches inside, for us to go through our CFD process. And we created a CAD model, and then decided to probably make the highest resolution fridge that we've been able to find. This is comparable to, the size of this is comparable to what we'd apply to motorsport to make sure that we find those intricate small changes in drag. We're talking about like fractions of a percent increase in or change in drag to this model. So hundreds of millions of cells. And this is an image of the mesh that we apply to these fridges to really get an understanding of how the intricacies of the aerodynamics and the thermodynamics of a fridge actually work. And let's be honest, a fridge isn't interesting. But when you get into the details of how it works, it can become really, really interesting, especially when you see how changes that you make to this digital twin, let's say, this simulation-based digital twin, can really impact the energy efficiency of that fridge and the knock-on effects to saving energy across the UK. So this is a slightly different simulation visual than I've shown today, partly because I'm not really allowed to show you what we're doing with fridges, because we're doing some pretty cool stuff. This actually depicts an air curtain. So this is at the front of the fridge. And now you probably won't notice it, but every time you put your hand into a fridge, you pass your hand through this air curtain. And it's defined as like a gradient in temperature change. So on the inside of the air curtain, there's a cold temperature. On the outside of the air curtain, it's meant to be warm, but let's be honest, it's not that warm. And here you see a lot of the airflow spilling out into the aisles. So again, we took to this as we would a race car, as we did the Eddie Stobart truck and the other trucks that we've been working on. and looked at all the different sensitivities and how we could develop components and geometry and configuration changes and operational changes to make this thing more efficient. And we tricked upon something that had a significant impact on the front of the fridge. So what this does, it tries to control the amount of turbulent mixing in the front layer of the fridge. So if you go down here, what's actually happening here, you've got cold air spilling out into the aisle, and because you've got cold air spilling out into the aisle, you have warm air spilling into the fridge, and that gets pushed around the fridge, and that's where a lot of the inefficiencies come from. And what we've done is created a component or product which tries to manage the amount of spilling out and spilling in. And that device is this. It's an eco blade. It retrofits onto the front of a fridge. And when we first designed this in CFD, it was fantastic. It was it had significant energy changes. So we were really excited about this product, this capability, this kind of innovative step on a well-known system or product, which we can just have a very quick change on. So we dusted down that old fridge that we were given, removed all the rest of the rats and everything else that was in there, instigated that into a lab test environment, and actually plugged on our eco blade and saved 20% of the energy of the plug. So it's an incredible step change in energy efficiency. And when you look at it in a supermarket itself, the great thing is it's almost invisible to customers. People don't really see it's there unless you're looking for it or are told about it. So this is the kind of the power of simulation, the power of CFD, aerodynamics and thermodynamics. If you can really understand what's actually happening in the airflow, you can make a significant step change in the energy efficiency. And the only way we were able to do that is to actually use very high levels of simulation, unsteady simulation, to really understand the turbulent mixing in the air curtain. If you remember back to some of the race car stuff and some of the truck stuff I showed you, that's the level I'm talking about. But wait, there's more. So we didn't stop there. We decided to have a little bit more of a look at it and design our own fridge. So if we could design the race-winning fridge, what would it look like? And we went at it and decided to completely tear everything apart from the shelves themselves and the produce. We left that in there, and we went out and designed our own fridge. And we came up with something that is quite interesting. Here it is. After we designed and developed it, we built 2 of them to really prove the fact that it worked as well as we thought it did. And you can lie at the base of this fridge and you don't get cold. It's incredible. We have people that come over to this a test lab and put their hands through this air curtain, and they can sense the difference. It's almost like an electric shock is the response. It's really, really interesting. And the energy efficiency of this is 40% more energy efficient than anything else on the market. But we're not fridge manufacturers, and we don't claim to be. We don't want to be fridge manufacturers. We want to use our simulation capabilities to create energy efficient improvements that can have a real impact on the planet. So we reverse engineered the main mechanisms within this fridge which cause this energy efficiency, and we are now installing them digitally and physically into OEM fridges. And every single time, it's really quite impressive. Every single time, the energy efficient numbers are at least 35, if not 45%, for every single type of fridge that we try on. And Waitrose recently have been world first, where they've installed these fridges into a store. And this has a very interesting kind of commercial impact as well. So they're not only energy efficient. My personal thought on it could be the warmest supermarket in the world. If you install these fridges at 40% more efficient into a store, you need significantly less plant to actually power it, to bring in the refrigerant into the fridges themselves. So when you take that into account, you can actually reduce the size of your plant by nearly double figures as a percentage which means that the return on investment of actually doing that is actually negative. So you save money compared to where you were before. So it's almost like you get this for free. It's incredible. So just top line figures. So it saves 40% of the energy of the actual at the plug, but saves between 30 and 40% of the store energy. That's what Waitrose are recording right now. It's really, really interesting, really incredible. And the knock-on effects of that, if it was installed across just the UK alone, it would save nearly 2% of the UK's energy. So that's a very interesting thought. So if you can have these types of innovations, the thing is, it doesn't need to be a game-changing step. We don't need to innovate a completely new way that we work. It just needs to be a big change on top of where we are. So if you think about what we need to do, we need to save 2% times 50. It's a bit ridiculous, but if there were 50 other ways where we can save a significant amount of energy like this, then we can have a game-changing effect on the CO2 emissions we create. And that's kind of where I want to leave you with. So Wirth Research, what are we all about now? I've told you about the journey. We've started off in motorsport, a bit of petrol heads, want to make a car go quick around a track. But we've then transferred and we're applying that now to innovations or industries where we can have a significant impact on our planet. And we believe that that life can be more enjoyable and more sustainable through our technologies. We're able to make buildings better to live, work and shop in, to make vehicles more energy efficient, and do all this while providing our clients with a compelling return on investment. It can be done, but we need to collaborate. We can provide some significant simulation capabilities to help people really see optimize the energy efficiency of products and systems. So if you're interested in talking, my email address is chris@wirthresearch.com. Be happy to talk to anybody who wants to listen. Okay, thank you.